is the last section in Unit 1. So in Honors Math Analysis, we don't cover all of Chapter 1 and very little of Chapter 2. The important topics were chosen. A lot of it's review, but they're important because we're going to continue to use them throughout this course and in calculus. So this section is rational functions. I'd like to say it's not a difficult topic, but what I think bothers people is that it's a fraction. A ratio is a fraction, and I think that's what bothers people. And this function behaves differently from all the other functions that we study. So I think that's the other area where people find difficult understanding it. So the domain, and it's going to look better when I give you examples. The domain of all rational functions is going to be all real numbers except what makes the denominator equal to 0. So I'm going to use the same function throughout this whole thing. If I had y equals 3 over x plus 2, the domain is going to be all real numbers except negative 2. Because if I put a negative 2 in for x, it's going to make it equal to 0. If you want to use interval notation, you may. It goes from negative infinity to negative 2, and then 2 to infinity. I tend to use this notation. The range is different. The range is usually all real numbers except the values for the horizontal asymptotes. So for this function, it has a horizontal asymptote at y equals 0. So it's going to be all real numbers except y is equal to 0. And discontinuities are vertical asymptotes and holes. And I'll explain that better in the next two where I talk about vertical asymptotes and holes. But you cannot have a value for a function at a vertical asymptote or at a hole. So that's why it's discontinuous. If I were to graph, well, let's look at this y equals 3x plus 2, 3 over x plus 2. This has a vertical asymptote at x equals negative 2. If I were to graph this, it's not continuous at negative 2. And if I grab the calculator and show you, clear that one. Your calculator does not graph a vertical asymptote because it is not part of the function. When you graph it, you need to mark it as a dashed line because that shows that it's not part of the function. So it looks like this. A hole is a point on the function where it's where the function, it's not a point on the function, a point where the function is not continuous. So this function y equals 3 over x plus 2 has a vertical asymptote. It does not have a hole. And the vertical asymptote is going to be x equals negative 2. It's a line. A hole would be an example if I had y equals, say, x plus 2 over x squared minus 4. So what happens here is I can factor the denominator. This x plus 2 that's common in the numerator and the denominator is where there's a hole. So the hole occurs at x equals negative 2, or the point negative 2, I'm going to plug it. If I cancel those out, I get 1 over x minus 2. Plug a negative 2 in for the x, and I get negative 1/4. So anytime you have a common factor in the numerator and the denominator, it's not an asymptote, it is a hole. So let's look at that and see what that looks like. Yeah. You can see the vertical asymptote at x equals a positive 2. And you can't see a hole at negative 2 because what happens, first of all, this is very pixelated. And it looks kind of jagged. It's supposed to be smooth. But we also need to look at the window. So I want to focus in at this negative 2, this point negative 2, negative 1/4. So I'm going to go to my window and I'm going to look from negative 3 to negative 1. And let's go from negative 1 to 1. And I'm really zooming in. You can barely see it, but right there, there's a space there. That's actual hole. Horizontal asymptotes have 3 different cases you can have. It's going to be a horizontal line. And the 3 different cases is when the degree in the numerator is less than the degree in the denominator. So what I'm talking about with degrees, I'm talking about the highest exponent. So this is 3. There's no x up there, so I could say this is x to the 0 power. This is x to the first power. Anytime this occurs, where the degree in the numerator is less than the degree in the denominator, your horizontal asymptote is always going to be y equals 0. If your degree in the numerator and your degree in the denominator are the same, so if I have a degree of 1 and a degree of 1, the horizontal asymptote is going to be a ratio of the leading coefficients. So it would be y equals 4/3. Anytime the degree in the numerator is greater than the degree in the denominator, so this is a degree of 2, this is a degree of 1, 2 is greater than 1, there's not going to be any horizontal asymptotes. If there's not a horizontal asymptote, there is going to be a slant asymptote. And the way to find a slant asymptote is using long division. So I've got this polynomial here, and I'm going to use long division. So x minus 1 is my divisor. X squared plus 3x minus 5 is my dividend. And the process is just the same as if you had numbers. If I wanted to divide 3 into, say, 25. Let's make it 257. So you can see 3 doesn't go into 2, but 3 does divide into 25 8 times. So I would put an 8 up here. So x does divide into x squared. I'm not going to look at this x minus 1. I just want to look at the x. So x goes into x squared. The way I think of this is x squared divided by x. And that's just going to equal x. So that's what's going to go up here. If I look at the number, my next step is to multiply. 8 multiplied by 3 is 24. And then I subtract these two. And when I subtract them, I get a 1. So what happens here is I'm going to multiply. X multiplied by x is x squared. X multiplied by negative 1 is negative x. But then I also have to subtract. And then I add x squared minus x squared is 0. That's exactly what I want to happen. 3x minus a negative x will be 3x plus 4, 3x plus x. So I get a 4x. With the numbers, the next step is to bring down the 7. And then I divide again. 3 goes into 17 5 times. 5 times 3 is 15. And I subtract, and I get a 2. So bring down the negative 5. X goes into 4x, or think of it this way, 4x divided by x is equal to 4. So I have to put a positive 4 up there. Multiply, I get 4x minus 4. And I'm going to subtract. If people make a mistake, it's usually at the subtraction, so just be careful when you're subtracting. 4x minus 4x is 0. Negative 5 minus a negative 4 would be negative 5 plus 4. So this gives me negative 1. And then to write this properly, this would be the remainder of 2. So that means I would have plus 2/3 here. Remainder of negative 1, so I'd have plus a negative 1 over x minus 1. But the goal on here is just to find the slant asymptote. So after the division is shown, my slant asymptote is going to be y equals the quotient, which is x plus 4. And I'll show you what that looks like. And what's important about an asymptote, it's what the function is approaching at the far ends. So if I graph this, let's just look at a regular window. It's kind of hard to see, but if I zoom out a little bit, let's change this to negative 50. I'm just going to go in every direction out to negative 50. It looks like there's a line there. And that line will be this x plus 4. See how it darkens right along there? If I go back in, there's the function. It's a rational function. And there's the asymptote. It looks as if the function is crossing or touching that, and it really doesn't. It can, but it usually doesn't. So let's zoom in a little bit further. Let's go negative 5. And I could go closer and closer and show you. So that's what a slant asymptote does. And then I'm not going to take time today, but during the live lesson, I'll go through an example where I talk about the zeros, which are also the x-intercepts, and the y-intercept. And finding those is just as simple as replacing a variable with 0 and solving for the variable you're looking for.